The question is
The question is, a plant has a transfer function. A plant has an open loop transfer function k divided by s into s plus 2. Design a compensator so that the following specifications are satisfied. Design a suitable compensator so that the following specifications are satisfied. Peak overshoot should be less than or equal to 18%. Then peak time Tp, that should be less than or equal to 1.95 second. This is our design specifications. We have to design a compensator, suitable compensator, using time domain approach. So in this type of questions, we can draw a rough root locus here. Since there are two open loop poles, s is equal to 0 and at s is equal to minus 2, the root locus, approximate shape of root locus will be like this. One branch will be starts from s is equal to minus 2 and other will start from s is equal to 0. After that, they will meet at the centroid, meet at the breakaway point, and there it will start moves asymptotically to the asymptotes. So this will be the approximate root locus of the given open loop transfer function. Now we have to find out what are the dominant poles. SD is equal to minus theta omega n plus or minus j omega d. So here MP is equal to 18%, so we can write it at 0.18. Now by applying the equation of MP, that is theta is equal to minus ln 0.18 divided by square root of pi square plus ln theta square. By applying that equation, by applying the equation of theta is equal to minus ln of MP divided by square root of pi square plus ln natural logarithm of MP square. By applying in this equation, we will get the value theta as 0.48. This is the value of theta. Now what is our peak time? Peak time Tp is given in the question. It is equal to less than or equal to 1.95 second. So the equation of peak time is pi by omega d, where omega d is the damped frequency of oscillations. Omega d is equal to omega n into square root of 1 minus theta square. So we will get the omega d, the specification omega d we will get from this equation. From this equation we will be able to find out omega d. What is omega d? Omega d is equal to 1.95 into 3.14. So omega d is 1.6 radian per second, and by applying the equation of omega d, that is omega d is equal to omega into square root of 1 minus theta square, we will be able to get the value of omega n. So when you apply the value, that is 1.6 is equal to 1.6 is equal to omega n into square root of 1 minus 0.48 square. The value of omega n, that is the natural frequency of oscillations, will be 1.88 radian per second. So we can write SD is equal to minus 0.9 plus or minus j 1.65. minus 0.9 plus or minus j 1.65. So that is the dominant poles, that are the complex conjugate pair located at the left hand side of S plane, LHS of S plane. So here you can see that we only have the specifications as MP and peak time. From that specifications we have to find out the dominant poles. So here from MP we will be able to find the value of damping ratio, that is theta, and from the equation of peak time, that is equal to pi by omega d, we will be able to get the damped frequency of oscillations, and from where we will be able to find out natural frequency of oscillation omega n. So if these type of questions are given, these type of questions can be given in different types of specifications. So if you have to find out SD or dominant pole, you need to know all the equations of time domain specifications, the equation of rise time, peak time, settling time, peak overshoot, etc. So all these equations you have to know, then only you will be able to find out the dominant poles. Okay, if you find out the dominant poles, what is the next step? Find out the angle theta p. The angle theta p is the angle of open loop system at S is equal to SD. So angle of K divided by S into S plus 2 at S is equal to SD. Here I am selecting the SD or dominant pole, that is on the upper half of real axis, that is minus 0.9 plus j 1.65. So when you apply in the equation, you will get the value of angle approximately equal to minus 180 degree. The value of angle theta b you will get approximately equal to minus 180 degree. So here you can see that the dominant poles that are lying on the root locus. The dominant poles are lying on the root locus, and since the dominant poles are lying on the root locus, the transient specifications are satisfied. Since the dominant poles are lying on the root locus, and we have to design a lag compensator. Since the dominant poles are lying on the root locus. So if the dominant poles are lying on the root locus, that means the transient domain specifications are satisfied. Then if you have to choose a suitable compensator, what we have to do? First we have to find out the dominant poles, and if we have to choose a suitable compensator in the question, if they specifies to choose a suitable compensator, we have to find out the angle theta p and find out whether the dominant poles are lying on the root locus. If the dominant poles are lying on the root locus, that means that the transient domain specifications are satisfied, and we have to design a lag compensator. So the suitable compensator here in this case is lag compensator. Now we don't know the value of K. So what we have to do? We have to find out the value of K using magnitude criteria. So that is step 3. Using magnitude criteria, find the value of open loop gain K. So magnitude of K divided by S into S plus 2 at S is equal to SD should be equal to 1. So when you apply this equation, this criteria, you will get the open loop gain K is equal to approximately equal to 4, 3.9, that we can approximate it as 4. So now our open loop system GP of S is equal to 4 divided by S into S plus 2. So this is our open loop system. Now in the question they have another specification. They have in the time domain specifications are also there, and there is another specification, that is KV, velocity error constant. In the question they have given velocity error constant that should be equal to 10 per second. The velocity error constant should be equal to 10 per second. So we have to find out the velocity error constant also. So what is the next step? Step 4 is to find out the velocity error constant. Find kV of the system. kV of the system. Now that is for open loop plant. We have to find out the velocity error constant. So what is that kV? kV is equal to, kV of the system now is equal to S into limit S tends to 0 4 divided by S into S plus 2, that is equal to 2. So this is our kV now. So we got the value of velocity error constant now. Now if we got the value of velocity error constant, what we can do? We can find out the transfer function. Next step is to find the transfer function or poles or zeros of the compensator. So we have required kV that is in the question. Required kV that is in the question as 10, and kV of the system now, or kV of the uncompensated system. kV of uncompensated system that we got as 2. Now we have the equation. What is the transfer function of the compensator? Kc into S plus A divided by S plus B. This is our transfer function. Now we have to find out the value of A and B, where A is the zero of compensator and B is the pole of compensator. So now we have to find out the value of A and B, that we can find out using the equation. A by B is equal to kV required and kV of uncompensated system. Uncompensated system, that is equal to 10 by 2. So we got A by B is equal to 5. We got A by B is equal to 5. Now the next step is choose B in such a way that it is very nearer to origin. So I am choosing B as 0.01. I am choosing B as 0.01. The criteria for choosing B is it should be very nearer to origin. That is the only criteria for choosing the pole of the compensator, pole of the lag compensator. So I am choosing B as 0.01. Now what will be our A? Our A will be 5 into 0.01, that is equal to 0.05. So we got the TF of compensator as lag compensator as Kc into S plus 0.05 divided by S plus 0.01. This is our transfer function of the compensator. Now what is the next step? We have to find out the gain K. So we got the transfer function of the compensator, and after that we have to find out Kc. Okay, now we have to find out Kc. What is Kc? Kc is the open loop gain of the compensator, and this also we can find out using the magnitude criterion, that is Kc into S plus 0.05 divided by S into divided by S plus 0.01 into 4 divided by S into S plus 2 at S is equal to SD should be equal to 1. This is the magnitude criteria. What is magnitude criteria? The magnitude of open loop transfer function. Now the open loop transfer function magnitude is Now what is the magnitude of open loop transfer function? So we have already designed the compensator. Now our open loop transfer function is changed into GC of S, that is our compensator, into open loop plant, that is GP of S. So this is our plant and this is our compensator. Now by designing a compensator, our open loop transfer function is changed into GC of S into GP of S. So by applying this magnitude criteria, you will be able to find the value of Kc, which will be approximately equal to 1. So in lag compensator, in the case of lag compensators, most probably the value of Kc, that is gain of compensator, will be most probably 1. So here we got the value of Kc, that is equal to 1. Now what is our steady state specifications? Our we have time domain specification as well as steady state specification. With respect to time domain specification, we have selected the dominant pole with respect to the time domain specifications, and now we have to check whether the steady state specifications are satisfied. The time domain specifications satisfied means the transient domain specifications, that is with respect to peak overshoot and peak time, the transient specifications are already satisfied. Since the dominant poles are lying on the root locus, the transient specifications are already satisfied. Now we have to check whether the steady state specifications are satisfied. That means we have to check the value of Kv now, that is Kv of compensated system, Kv of compensated system, that we have to check. So how can we check the value of compensated system? Kv of compensated system, that is the Kv of compensated system is equal to limit s tends to 0 s into GC of S. Now our open loop system is GC of S into GP of S. Now our open loop system with the compensator, our open loop system is changed into GC of S into GP of S. Now it is equal to limit s tends to 0, Kv of compensator system is equal to S into S plus 0.05 divided by S plus 0.01 into 4 divided by S into S plus 2. Now if we apply in this equation, we will get it is equal to now we can see it is equal to 10. The Kv of compensator system is equal to 10 now. So that means our steady state specifications are satisfied. By designing a lag compensator, our steady state specifications are also satisfied. So these are the design procedure for designing a lag compensator using time domain approach. Thank you.